So who forgot we didn't have a lecture yesterday and came here? Be proud. Be proud. Who came all the way here before? 1, 2. Whole table, almost a whole table over there. Yeah. So in my defense, it always said on the syllabus we didn't have a lecture yesterday. So it's not like I canceled it. And I really meant to send that reminder announcement earlier in the morning. In fact, I typed it earlier in the morning, but then realized I didn't send it until it was like 10 of 11. So I guess we all own that, right? Everybody owns that. Today, I still haven't decided if I like this room. Pretty sure I don't like this room, but I'm not certain it's the room's fault. It could be my fault. I'm used to teaching to people like that, right? And I thought it would be really cool to teach to people like this, but it's dizzy and I don't know. I don't know I'll choose this room again, but we're stuck with this room for now. I'm going to go back and forth between some slides and my my document camera here. If I appear to be talking about the stuff on the paper and the screen is showing the slides, somebody remind me before I get too far into the conversation. And likewise, if I feel like, if you think I'm talking about the slides and the paper is up on the screen, just let me know. And that'll work. And as I'm writing stuff on the paper, you'll note that I can't spell. My younger daughter, she got a spelling test home. My wife had to sign it. She had a 56 on her spelling test, and neither myself or my wife cared that she got a 56 on her spelling test, right? But the next day, she had planned out a study program for herself so that she would never again not get a good grade on a spelling test. And I'm like, wow, she did not get that gene from me. Because when I was in school and I realized I couldn't spell very well, I convinced myself it wasn't important, which is a valid coping mechanism for a lot of things, right? But I think this is plugged in. Just, Maybe now it's plugged in and it won't go to sleep. Now it's plugged in and it won't go to sleep. Cool. I don't know. I think the spelling thing is overrated. The purpose of language is to communicate, right? If you understood what I meant when I wrote it down, have I successfully communicated? Therefore, it doesn't matter. I spelled it right. Okay, but today I want to talk about CNC machining and prototype manufacturing. I think everybody in the class now has had a chance to be in the lab and do something. There may be a couple of people that have still haven't gotten in the lab because of being in isolation or having some other reason they didn't get to class. But I think everybody's had a chance to be in the lab. And I think about a third of you have had a chance to operate a CNC lathe or to be there when it was operating, right? And I think all of you have had a chance to be at a mill. What's the difference between turning and milling? So most of you have seen the lathe. What's the difference between turning and milling? Yes?
In a mill, what's spinning, and on a lathe, the part is what's spinning.
That's the primary difference, right? In the mill, the tool spins. In the lathe, the workpiece spins. Now, if we're spinning the workpiece, who's had ES1310, the CAD class, or who's used CAD software before? Or like, I shouldn't say CAD software. I should say solid modeling software. Because it's a little bit different, right? You don't have to do solid modeling to do CAD. But pretty much everybody's seen the solid modeling software. I think all of them have this revolve feature, right? So you like make a line and you click revolve and then it makes a solid where that line sort of defines the outside shape. So shapes that you make in the software with the revolve feature are very well suited to CNC turning, right? Because they're axisymmetric that way. Now, sometimes you're going to make a shape that has some features, a part that's got some features that are axisymmetric, so you can turn them, and some features that are not. You might then put it in a lathe to make some of the features, put it in a mill to make some of the features. You may put it in a machining center that can do milling and turning in the same machine and the same setup. So there's a bunch of different ways that you can do that. But I want to talk about CNC machining. So I guess first let's talk about machining. Oh, what a great segue. I totally thought that was the next slide. Wasn't certain, but I totally thought that was the next slide. So we're talking about machining. And so machining is a material removal process. What we're talking about when we're talking about milling and turning, we're talking about a material removal process by large chip formation. Who's seen the chips from the machining operations? How big are they? Like hold up your fingers and say how big they are. The chips? They're pretty small, right? But in the physics of machining, those chips are considered large. What do you think would be a process that would make small chips? Yeah. Grinding or sanding would be a process that makes small chips. And so when you see, and if you've ever used sandpaper or something, the dust that's left over, those are little tiny chips. But the physics was the same as we see in milling and turning. And so what we see here in my fancy drawing, the cutting tool is this green bit. The cutting edge of the tool. So if you were in the machine, don't do that, by the way, don't climb in the machine. But if you were in the machine and you were seeing this happen, sort of the sharp edge of the cutting tool that goes through the workpiece material, in this picture, at this spot right here, at that corner, we're looking straight down that edge. So if you had like normally I have a Leatherman on my belt here, and I could pull it out and show you a knife blade. But if you were looking down the knife blade edge, we're looking straight down there. So the chip has width into and out of the screen and thickness up away from the cutting tool. Does that make sense? So as that tool moves through the workpiece material, it's, has anybody ever put butter on toast? Anybody ever put butter on toast when the butter was kind of cold? That sucks, right? Better when the butter's warm. But when the butter's kind of cold, you take the knife and you sort of scrape it across the top of the butter. You can, some people do. Some people go all in and they slice off the end of the butter. I'm more of a slice off the end and get the thick pat. But you've seen that, right? It's the exact same process. So here our cutting tool is like that knife. And it's scraping material, in this case, in the picture, it's off the top of the workpiece. So if we were in the lathe, where our workpiece is spinning around, and the cutting tool is moving in and out along the side of that to make a revolved kind of a feature, an axisymmetric feature, what orientation would you say this picture is? So if you were in the lathe and you had to describe where is the tool that you're looking at, can somebody visualize that? Yeah. Yeah. Let me switch the view here. See if I can make this happen. First, I go here. And I'm totally not sharing the screen right now. Sorry, people at home. You didn't get to see the screen. But believe me, there was pictures on the screen. Share. I want to share screen, but I want to share a window. This one. All right, now Command Tab. I want to come over here. I want to share an app window. This one. That didn't seem to do what I wanted. Stop sharing desktop. Share app window. This one. Oh, come on. Could I share this one? But not the other one. But it's real. I don't know. Stop sharing all. Share app window. Share this one. Huh. Okay, maybe I won't do that. Desktop. All right, you guys can see what I'm writing now, sort of. And you can see if anybody makes a comment. I probably should start with clean paper. Okay. What was I talking about? Now I'm all confused. Yes. Orientation of the workpiece in the lathe. Okay. So I've got my cutting tool, right? I showed the cutting tool. I got the workpiece. The chip is going up like that. Right, so the chip is moving that way. The workpiece is moving that way. Can you guys see any of that? Okay. Maybe I'll try to zoom in a little bit. There, zoomed in a little bit. All right, so the workpiece is moving this way. The tool is here. So what moves in the lathe? Yep. The workpiece moves in the spindle. And so the workpiece spins around in the spindle, right? Workpiece spins around like this. So so the tool moves too, right? It moves in and out. to make different diameters, and it moves along the z-axis to make different lengths. So it moves in and out in the x direction, moves left and right in the z direction. So the tool moves too, but the cutting happens because of the rotation of the workpiece. So the workpiece rotates around and it comes in contact with the tool, the chip forms and slides along the edge of the tool. And then you move the tool over when the tool moves, right? And now there's a new bit of workpiece that's going to come along, make a chip, and slide along the edge of the tool. And so if you think about that, if you've got your round workpiece here, and you've got a tool like this. So in this picture here, this point right there, and we're looking down the edge of that point right there is this edge of the tool. And so the tool's feeding in this direction. And the workpiece is spinning in this direction. So for each revolution, the tool moves over a little bit. So as the tool moves over, and it's moving continuously. It doesn't stop and start, stop and start. But for each revolution, the tool moves over a little bit, and chip forms and flows off in that direction. So we do that in a turning operation. That's where the chip flows off, and so the chip goes off like that. All right, so you're looking, in this diagram, we're looking down the edge of the tool, and it's the rotation of the workpiece that's making this happen. All right, so what about in milling? So this is turning. What happens in milling? At least it's easy to switch back and forth between the two now. What happens in milling? Not that one, this one. That view is better. It's exactly the same physics. So what's the cutting tool look like in milling? Yeah. So the tool is spinning, and the tool has these spiral flutes on it. If we looked at the end of it, it's maybe got this one, we'll say 3 cutting edges on it, right? And so these edges here, they spiral up the tool. And so where's the cutting happen? The cutting's happening either right here on this bottom edge, if we're going down into the material, right? If we're going down past the material, it's happening right on this edge down here. Or it's happening as this spiraled flute moves side. So you could think of the rotating of the workpiece in the lathe. So the rotating of the workpiece in the lathe brings the cutting, makes the cutting happen. The rotating of the tool in the mill makes the cutting happen. It's the spindle rotating, in both cases, in the mill and the lathe, that makes the cutting happen. And so the feeding in the lathe moves the tool over, so there's a new bit to cut when it spins around. The feeding in the mill moves the tool over, so there's a new bit to cut as it spins around. So it's the same exact physics, it's just happening in a different spot inside the machine tool. It's a lot easier to mentally visualize the lathe one, right? Does that make sense? Turning in the lathe. Next week, we're going to talk about how we model these processes, how we know, like there's, especially if we look at this one, right? If you look here, where that chip is, it used to be workpiece material, and now it's chip. That spot where the transition is, there's a lot of energy there, right? It takes a lot to take metal and make it not be attached anymore. Who's ever done that? Like, You break a piece of metal or something. It takes some energy to do that, right? Okay, so if I go back to the slides, let's see, stop screen share, share, slides. No, I don't want to do that. Oh, that's cool. I didn't know I could do that. Next time, share, screen share, this, share. Now go to this page. All right, I think the people at home see the same thing we see. If I go back to the slides here, so let's take a look at, relative motion, yeah. Here's the picture. Oh, this is a cool video. Let's watch the cool video. Did you guys ever have like videos to watch in school? Like especially when you had a substitute teacher? They'd play the videos. Did they wheel in the cart with the TV on it? And then, yeah, yes, no? Yeah, they wheel in the cart with the TV on it. And then did they have DVDs? You had a VCR? Yeah. So when I was in school, they wheeled in the movie projector. Right? And you had to feed the movie film through the wheels and all that stuff to do this. So when this video was actually originally made, it was totally the movie projector kind. Let me back up a little bit. So what we see here, and so it's a turning operation. You can see the turning operation. They're spinning the workpiece. They're moving the tool through the workpiece. Back up a little bit. Moving the tool through the workpiece and feeding across the front face of the part. And so if you zoom in on that as it's happening, you can see that it's actually changing. So you see the little boundaries between the like the dark and the light stuff in here. You see that they're all like scrunched up together in this part, and they're all sort of amorphous over here. So it's actually changing the structure of the material. It's changing the internal shape of the material as it does that cutting. This is my fancy animation. Check it out. I was very proud of that. I did that animation. And now it looks like the picture I drew on the paper. It's going to look more like it in just a second. Yeah, tool. So exciting. Oh, man, it's too slow though. Workpiece. Yeah, chip. Oh, come on. I don't know why this is so slow. So that's all of machining. All machining is this process. Even sanding, like sanding and grinding, it's this process just on a smaller scale. So on a lathe, you typically have one cutting edge, right? In a turning operation, there's typically one cutting edge. In a milling operation, there's typically 2 to 5 cutting edges, like the flutes on the end mills. A lot of the ones we use are 3 cutting edges. Sometimes we'll use a single flute cutter, especially for like an engraving or something. But there's usually a couple, a few cutting edges in milling. In a grinding process, each little piece of grit on the sandpaper, for example, is a cutting tool. And so there could be thousands of cutting edges in a grinding process or a sanding process each time it goes around. But the physics of what's happening is exactly the same. All right. I think if I just hit the button, it'll go to the next. Oh, check that out. It's amazing when technology works. All right, so this is our turning again. See if I open this up bigger. Oh, no, I don't want to do that. I'm not logged in. Wait, why am I not logged in? Switch account. There, now there's no ads. All right, so this was our turning operation, right? So in this case, we're turning the outside diameter of the workpiece instead of the face of the workpiece. And the other one, we were turning the face of the workpiece Here we're turning the outside diameter of the workpiece. So you see, as the workpiece comes around, it hits the edge of the tool, it forms that chip. And this is kind of boring. Skip ahead, turn faster. Turn faster. I guess there's nothing exciting there. Come back over here. Now here's a milling operation. All right, come on. I don't care about your stupid CGI stuff. All right, so if we are going to do, what's today's topic? So CNC machining, that was part of it, right? It was 2 parts to today's topic. What was the other part of today's topic? So we have, what makes so we talked about machining. Milling and turning is machining, right? What makes it CNC? Because it said CNC machining. What makes it CNC? Yeah. Prototyping was the answer to the first question I asked, but I stepped back and asked a previous question. Yeah, so CNC machining and prototyping is what today's about, but what makes the machining CNC instead of just machining? Yeah. It's controlled by a computer. It actually stands for Computer Numeric Control. Of course it uses numbers. That's what computers do, right? They actually add ones and zeros. That's what computers do. So of course it uses numbers. Before we had computers directly controlling them, they invented this thing called Numeric Control, and it was NC machining. But it really was, you used a computer to create the steps for the program, and then they took these like note card things, and they put holes in them at different locations. Then you could feed those cards into the machine tool, and it had a little computer inside that would read those cards that you fed in. Anybody ever seen a computer that worked on paper cards? Yeah. Old school, right? 1947 or so was the first NC machine tool. So old school computers. They, when I was a student here at WPI, when I was a grad student here at WPI, the only CNC machine tool that we had was an NC machine, an old NC machine that somebody had retrofitted to be connected to a computer. So progress has been made since then. Or I'm really old. You can make your assumptions either way. All right. So all that makes it CNC is the fact that a computer is controlling the machining instead of a person. So I typically refer to manual machining, which is the common non-CNC version of machining. I call that Etch-a-Sketch style, because the way you control it is by turning handles. Okay, but that's the only thing that makes it special. The physics of the process is the same. All right, so why are we talking about CNC machining and prototyping in the same statement? Yeah. So you can rapidly rototill. You can rapidly prototype things using CNC machine tools. Why not just 3D print them? Right? I mean, in 1947, it was because we didn't yet have 3D printers. Okay, we do now. Why not just 3D print your prototypes? Yeah. This might be more representative of the final strength of the part. Okay. Why not 3D print your part? Yeah.
It's a lot faster to CNC machine than to 3D print.
It's faster to CNC machine than it is to 3D print. Stand up if you agree with that statement. Faster to CNC machine than it is to 3D print. Wow. See everybody that agrees. All right. You're not standing. Is it just because, I mean, the other day when I asked you're not standing, it wasn't you necessarily, but somebody just said I was just too lazy to stand up. That's not your reason?
No.
No. Okay. You guys can sit down, but go ahead and explain why you think it's faster to 3D print than it is to CNC machine.
Well, I honestly don't know if it is or not.
Oh, you don't know. Okay. That was fair.
Because like I think it depends on like the size of what you're creating.
It's going to depend on a lot of things. So stand up if you think it's faster to 3D print. Really? There was more people sitting than that, wasn't there? Stand up if you were sitting when I asked the last question. Yeah. Oh, now you changed your mind. You can stay up.
I misunderstood the second question. Sorry.
All right. So why is it faster to 3D print?
I think it depends on the scale of the object.
All right, and that was sort of your answer too, right? It depends on the scale of the object we're using. Why is it faster to 3D print?
I just think like with CNC machining, I feel like all the code and stuff and setup is going to be a lot more time than 3D printing.
All right, so he said, it's going to take a while before my fingers are wet. All right, so you said setup and code. Right, so that's going to take a long time, whereas with the 3D printing, you just kind of press, right? Yeah, so stay standing if your answer is different from, it depends on the size and it depends on the setup and the code. So you should sit down because your answer was that. I'm trying to see who has a different answer. All right, so why do you think it's faster to 3D print?
Well, also it sort of depends on the how you're building. Like, you might need to use two different machines to like get the final result of whatever you're making. Like if you 3D print something, it literally just starts from the bottom and builds the whole part. And then like unless like maybe support material is really all you need, and then like again there's no coding.
Okay. Is there anybody that has a different answer than, let me summarize yours in, how do I summarize it? Then it depends on the number of processes and the complexity of the part, right? Yours was, it depends on this. It's very similar, but not quite the same. Yours was more about size than complexity. Yours was about just the fact that you have to do setup to do CNC machining and you don't have to do as much setup. All right, so you're still standing. You got a different answer?
Yeah, I was going to say it could also depend on the type of 3D printing.
It's going to depend on the type of, so what material you need the part to be made out of, you mean? Yeah, so it's going to depend on that. You can sit down. Thanks. Thank you guys for playing my game. Let me, is this going to work? If I switch back, I go here. And stop screen share, screen share, window, this one, share. And then make that one be in front. Okay. So the things we talked about were setup and creating code. The size and shape and material. So I guess what is it? Size and shape and material of the thing that you're making is going to determine which one is faster, right? So I think that this is true. So especially with simple parts, I would say that it is way faster to 3D print the part if you don't know what you're doing. Right? If you have to learn the steps, if you have to learn how to do the setup, and if you have to learn how to do the coding, the learning curve is shorter with 3D printing as long as your 3D printer just works out of the box, right? I mean, I have personally never purchased a 3D printer that just worked out of the box, but that's because I allow students to influence my choices when I'm picking 3D printers. And I don't know, they like to, I assume that there are 3D printers that you can just buy it and unpack the box and put an STL in and the part comes out. I assume that exists. I've never experienced it. In my experience, we buy the ones that get like the box full of 80/20 and you have to bolt them together. And that usually takes some learning curve to get started. But yeah, so here on campus, if you want to have something 3D printed, what do? You get, yeah.
You go to a 3D printing lab and then you put in your.
Do you even have to go there? Can't you just go to the website?
Well, you go to the website, but then you have to like put it in yourself and pay for it.
Oh, you have to load it yourself, and I know you have to pay for it, but I thought you did the whole thing from the website. It's all remote, right? You don't actually even have to go in the room if you've got an STL file. Who's ever printed something and it was crap? Anybody who's ever printed something, right? Right, because it does depend a lot on how you set it up, how you decide to slice it. So this code, so the setup is pretty simple, right? You don't have to put a vise in the machine. You don't have to make sure that you use the torque wrench. Who was there for the non-torque wrenched Y blocks? It happened to a couple people, right? You guys dropped the class after the first day of lab. Were you there? You were there though, right? What happened when the very first day in lab, your lab instructions for that Y block, it said to use a torque wrench to tighten the vise. The person who set it up forgot to supply the torque wrench. So the person who went, one of the first couple people that went, there's a wrench handle that's just at the machines, but they had no perception of how much force to apply. We're not even sure they applied force. But so what was the result? Oh, they had a torque wrench later in the day.
The piece like stopper or whatever it's called.
Yeah. Oh, okay. I remember. So that particular one is so the first thing that happened when the tool came over, I mentioned there's a lot of energy at that cutting zone, right? Well, so force times velocity is power. Is that right? So you just think about, energy and power are related with a time factor, right? So there's a lot of force because there isn't a whole lot of distance, right? There's plenty of velocity. There's a lot of force going through there. And so it tried to pick the part up and shove the part sideways. It shoved the part sideways hard enough that it moved the little part stop that was supposed to tell you where to put the piece. And there's a reason that we have the torque wrench thing in the instructions. In a previous iteration of an ME1800 lab, doing the same exact thing, people didn't tighten the vise enough because they didn't know how tight to make it. It picked the piece up. It successfully picked the piece up, bounced it off the back of the machine, and then broke the glass window in front. I mean, it just made a crack. It didn't like come shattering out or anything. It wasn't like a movie break, but yeah, those are not cheap. The following term, ME1800 first lab, picked the piece up, bounced it off the side of the machine, broke the glass. The term after that, it said to use a torque wrench in the instructions. Right, so with 3D printing, you don't have to bother with all that fancy setup stuff, right? You sort of press the button and either it works or it doesn't work. And if it doesn't work, you can fiddle with the settings and the spacing and all that stuff. So it's often quick to get something, especially when you don't know how to do the setup. Right, so if you had to set up the machine to make, I don't know, make a pen holder, something I could put this pen in and it would sit there on my desk. So like a block with sort of a hole partway through it, a pocket in it that I could put this pen in. If today you had to set up the machine to do that, could you figure it out? So if somebody already made the program for you, so you didn't have to do the program part, right? Because that's pretty automated with the 3D printer. It actually can be very automated with the CNC machining too. There's automation. We don't use those automation features in ME1800 because we want to teach you the sort of the engineering part of it. But in a facility that does this kind of thing all day long in a job shop kind of place, they may have automation steps set up in the programming stuff. So you basically drag and drop the file. So here's my solid model, drop it on the thing, and it spits out the code to the machine. You don't have to do all those steps. Well, you guys have to. But I'm just saying that people in industry don't have to because somebody figured out how to automate it. So you can automate the programming side of it just like you do with the 3D printing. But if you had to set up the machine to make a little block, do you have enough information not to easily do it, but could you guys figure it out? Like if you had to do your MQP and you needed to have something machined and you had to show it to your advisor by the meeting at 4 o'clock tomorrow afternoon, and you didn't have anything else to do between now and 4 o'clock tomorrow afternoon, could you make it happen? I'm guessing you could. Would it be way easier to just go to the web form and fill out the thing and 3D print it? It'd be way easier, but you could figure it out. Would you believe that I could set up the machine to make that part in about 15 minutes? Right? So there's skill, right? So I have, well, in this one little tiny area at least, I have more skill than you do about setting up the machine, right? But by the end of ME1800, you'll get past most of that learning curve. Right? The thing about learning curves is they're like asymptotic at the top. So you do most of the learning in the beginning, and then you get a little bit incrementally better as you keep going. So by the end of the class, you'll be able to do that. So it's going to depend not just on what it is, but it's going to depend on who it is too. For me, I would have to find the web form. I would have to figure out how to fill it out. I would have to remember what account number was I going to pay for it with, because I'm totally not going to use my money. And all that stuff would be way more hassle to me than just to go set up the CNC machine. So I would just make it. But it's going to depend on the person and the stuff, but it's also ultimately going to depend on what do you need the prototype to do. So why do we make prototypes? First off, what is a prototype? What makes something a prototype? It's a thing, right? Who's never used the word prototype in a sentence? So we've all used the word prototype in a sentence. So what did we mean when we said prototype? Yeah.
It's not the final product.
It's not the final product. We're making it to see, is this what we want to make? Often that's the reason we do prototypes, right? Maybe we were making it because we want to see, does the shape fit into the carrying case that we made for it? Like maybe we're making a carrying case for our violin, right? So I would probably, depending on how expensive the violin was, I might make a prototype of the violin in order to test the prototype of the case, right? Right, but you want to see, does it fit? Maybe, so my first experience with 3D printing, I told you guys about this? I was a young engineer at a startup company making medical devices. We were going to be the Coca-Cola of our industry. That was the plan anyway. And there was electronics in it. There was a box, and then it would sit on your nightstand. And so it had to look cool because we were selling it to people that were going to then let it sit on their nightstand. And so we got this company down the street to 3D print us what the box was going to look like. That was the coolest thing to me because I could go pick it up. But it was all because we just wanted to see what's it going to look like. What would the thing look like? I think we spent $15,000 to get this, and it was totally not structural. This was early days of commercial 3D printing. You had to be gentle with the thing. It would break if you dropped it. Not the finished product. They were all injection molded. Okay, so it depends on what, but we do prototyping to try the part out. Why CNC machine instead of 3D print then? So we could do either. Why would you choose CNC machining instead? Yep.
Well,
So you're likely to have a closer match to your finished part by size and tolerances and things like that. So you can achieve tighter dimensional tolerances with CNC machining than with 3D printing typically. You can use the same material that it's going to be. There's only certain materials that you can 3D print. There's more and more materials that you can 3D print every decade, every year, I mean. Like every month, it seems like they come out with a new method of 3D printing. So they're catching up. But also, so if you were making the little bracket that holds the wing on the airplane, and they make these, and they CNC machine little things that holds the wing on the airplane. We don't know that much about 3D printed materials. We know what the shapes they can make are. We know how they come out, but we don't know how strong they are long term. So airplane wings vibrate. Anybody flown on an airplane and looked out the window and seen the wing doing this? Well, just think, and you know it's doing that at a smaller frequency too, right? So it's got the big thing that you can see, but there's also little vibrations because you can feel them in the seat. So who's taken a paper clip and done this and broken it in half? So you're fatiguing the paper clip by bending it back and forth. Well, that wing on the airplane is getting fatigued also. And that little bracket that we made. So it turns out we've spent, I don't know, the last 100 years or so making airplanes with CNC or with machined parts. We've got a pretty good understanding of the fatigue life of those machined parts. We know how to design those parts so that they don't fail and have the wing fall off halfway across the ocean. Because it sucks when one of the wings falls off an airplane. Like in general, it's a severely heavy landing when that happens. As a little kid, we had this flight simulator software for the first computer I had. And you could type on the little membrane keyboard thing and you could fly in there. And when you would crash, it would say severely heavy landing. So yeah. All right. So you may care about the material properties of your prototype because you may want to know, is it going to last? WPI is actually one of the places at the forefront of understanding the materials properties of those 3D printed things. In the lab every day, we've got 3D printed stuff that we're machining into specimens so that we can break them, so we can see how long it takes to break them. But and so it's getting better. All this stuff is getting better, but CNC machining is probably the most prolific way of making finished good prototypes now in the US. So that's why we're talking about this. I think we got today a good understanding of sort of what is machining in the fundamental sense, what makes it CNC, and why we might want to use CNC machining for prototyping. Besides the fact that we have a lot of really cool CNC machines here at WPI. So you may want to use it just because you have access to it. There's still a few people that need a group, I think. Is there anybody here that needs a group? You don't have a group yet? Does your group have a spot in it? You guys one group mainly at this table, or is it just 5 people in your group? Is there any group here that has less than 5 people? Your group has less than 5 people? Can you meet him? It was a him, right? I can't tell with the masks these days. Can you guys meet at or like right now and sort it out so you can join their group? And I will check online because I think there's a couple people that emailed me said they're having trouble with the groups. Tomorrow I'd like to just do a quick update from each group. Maybe I'll do a thing where you guys can, should I do a thing where you guys could submit something? That'll be faster than going around the room and having you tell me, right? All right, so I'm going to do a thing where you guys submit your, because we got to do a thing where you actually get an online group. Yeah, tomorrow we're going to talk about how we're going to submit that. Okay, and how we're going to do it. I'm going to demonstrate that. And then we're going to continue talking about, what do we talk about tomorrow? What do we talk about tomorrow? Oh, cool. All right, so we're going to talk about what goes into making the program to make your parts tomorrow.
Has 6 people. Should we split into 2 groups of 3?
That's fine.
That's okay.